The following presentation was recorded at the 2025 Southeast Linuxfest in Charlotte, North Carolina. It is licensed under a Creative Commons license. For more information on the Southeast Linuxfest, visit www.southeastlinuxfest.org. Come join us next June.
So a few brave souls here to listen to a long presentation. I have a break scheduled in here, so I know that long things can be difficult to slog through and hold your attention the entire time. I also apologize for the projector. It's what it is. So if there's largely it's pictures, but if there's text, like I have an agenda, and we are not going to be able to read the agenda. So not that I wouldn't sit here and read the agenda, but this is just to give people an idea of like where we are, and we'll break somewhere in this vicinity, and it just kind of gives you general topics. So I'm not gonna read through that, but like obviously we can't look at the agenda. So, well, I'm gonna kick off. Hopefully everybody can hear me. Thank you for coming. I hope this ends up being useful to you. So this is an aid. I don't care whether I get through all of this or none of this. If you guys just want to have a conversation and ask questions, I'm here to serve you. I'm not here to like talk at slides, right? I want you to get whatever it is you need out of this. So if we want to have a dialogue, fine. If everybody's shy, I'm just going to go through this. We're going to talk about Kubernetes and how it works, but this is more like a survey. So what I mean by that is you can go anywhere on the internet and find like how to deploy something on Kubernetes. Here's like what a pod YAML looks like, or all that kind of stuff. This is more, how do all the pieces work together? If I'm an administrator, what sort of things do I need to look at if I have a problem? In an hour and 45 minutes, you can't cover everything. And it's also kind of boring to be like, oh, look at this YAML, and here's this YAML, and if I do this thing, a pod comes out. That's kind of boring. So I have an agenda. We'll get to whatever we can. I know you can't see it. I'm sorry. There's not much I can do about it. We'll take a break somewhere in this general vicinity. I don't know, somewhere in that way to give everybody a brain break. So we're going to start with a little bit of history. So ultimately, we need to start with a problem statement. Why are we interested in this? So ultimately, we're trying to provide a way for applications to be run at scale with some level of self-healing. That's what we're trying to achieve. We want application stability. Well, how do we get there? Well, if you think about where we came from, when I started, uptime was king. That was the thing everybody was really proud of. Like, I got 900 days of uptime. Nowadays, you'd be like, you haven't rebooted your server in 3 years? Like, are you crazy? But when I started doing tech, that's what we did. And we deployed everything to like a giant metal server. And we deployed our monolith. And that worked for a time. While demand was low, it worked. And then we realized that in order to handle more demand, we had to scale out. What did we do? We invented this thing called virtual machines. For the purists out there, yes, BSD did stuff like this in jails and all that sort of stuff first, but the mainstream adoption came about through VMs. And we basically just took our monoliths and shoved them in VMs and then spread them across a bunch of servers. And that was our way of solving the scaling problem until we didn't. So then we ended up having like, hey, you know, when I bundled that giant Java file that had an embedded database and the web server and everything, didn't scale super well because I had to basically clone that VM. And so we started to figure out that if we separated the various bits, we had a little bit of a better time managing things. But we still shoved them all on VMs. It's a progression, you know. When you look back, you think, well, that's kind of silly. Why did we do that? Like, what did we achieve? We basically still shoved all the components onto a machine and called it a day. Like, if you look at how Confluence, for example, a very famous wiki from Atlassian, kind of deploys itself by default, it installs Postgres, and then it installs Apache, and then it installs the jar files and Java all onto one machine. So it still broke it up, but just shoved it all on one machine. And during this time, we started to get into this idea of APIs and database action and splitting these apart. And this idea of a microservice was born. If you're not familiar with a microservice, essentially the way a microservice is, if you can think of something like an online store, okay? When you go to Amazon or wherever, or your store of choice, when you go there, it's not just one application that makes up the entire thing. From your perspective, it is the web app. But you have a checkout service, and you've got a recommendation service, and you've got a cart service, and you might have ads. And if you're international, you've got a currency service, and so on. So from your perspective, you're coming from here, you hit the internet, and then you go to Amazon or wherever. And this is broken up into all these individual pieces, which are legitimately all their own programs. And that is all working together in order to provide you the service that you are hitting. And there's just like, I made up some languages, like some of it's in Go, some of it's in Python, some of it's in C#, and so on, just to illustrate the fact that microservices don't have to even be written in the same language. They just have to produce a result and work together. Okay, so what does that have to do with where we're going today? So we have a microservice, and about the same time, so we're splitting up our application. We're getting a better idea of how to make our applications more scalable by realizing bottlenecks in the application. About this time, we start seeing heavy development of something called Linux namespaces. And what a Linux namespace is, very briefly, I have an entire series on just Linux namespaces. So I'm going to try and condense this down into like 20 seconds. But a Linux namespace is essentially an area inside the kernel that is blocked off from all the other processes. It's essentially like a little sandbox inside of the kernel just for networking. And that's how you can have a whole bunch of containers on your system and them not step on each other in networking or whatever. So you've got networking and user space and all of these different components that go to make together an operating system. And jointly, these are called Linux namespaces. So then somebody got the bright idea of like, okay, I got this thing in the kernel that allows me to keep things separate. And I've got this microservices thing over here. What happens if I put them together? And we come up with this idea of containers. And it was awesome. We're like, great, containers, yay. And what did we do? We shoved monoliths inside of containers and decided that was a good idea. But ultimately, that didn't scale. And we ended up just cramming our density back down onto single boxes. Like, I watched this whole evolution. We moved from metal to a bunch of machines, and then we contracted back to a single machine because now we can have the density, and now we've gone back out to spreading across multiple machines again. So our problem statement now is, now that we're in the container era, great, but how do we actually manage things appropriately, right? We want things to self-heal. We need things to be a little bit more dynamic. We need to be able to scale out this one and not that one, because you don't need to scale your database every time you need more Apache workers. That would be a waste of resource. And so how do you go about doing that? And largely, the industry has kind of settled on Kubernetes. So OpenShift is a distribution of Kubernetes. We're all familiar with distributions if you're at a Linux conference. There are plenty of different distributions for Kubernetes. So a lot of what we'll talk about here is going to apply across whether you're using Rancher or OpenShift or vanilla Kubernetes. And if there's a difference, I will tell you like, hey, this is OpenShift only, or most of what we'll talk about is all Kubernetes. So great. I've decided on a direction. I know what my problem scope is. I've decided like I'm going to go down a specific path. The next obvious step is let's go ahead and do the installation. So as I'm deciding on my Kubernetes distribution, one of the things that you look at is like, how is it that I get a working cluster going? So in general, you've like, yes, I'm going to do some sort of orchestration. I'm not just going to leave Docker or Podman on a machine. What type of Kubernetes distribution do you want? So you've got vanilla Kubernetes, and vanilla Kubernetes is flexible, and it's legitimately awesome. I teach labs about how to stand up vanilla Kubernetes and get it running and customize it. The problem with vanilla Kubernetes is that, not problem, one of the good things about it is you can find patterns for your use case out there most of the time, which means someone's tread the path and just, you've got a blog article and you just walk top to bottom and boom, you've got yourself a cluster, right? And this is especially awesome because you get to see that you've done something and you don't necessarily have to have all the pieces in the world. This is like your Legos where you've got a set and you've bought the set and you're just following the directions to plug it in. However, most of the time, vanilla Kubernetes is like a giant tub of Legos that's just been dumped on you because the way I need to use it is not the way you need to use it. Or maybe I have an enterprise contract with Nginx and you don't. So what do you do when that is a key part of the blog post is how I'm constructing my environment around Nginx and you don't have that agreement. So vanilla Kubernetes setup can be really challenging because you have to pick all of your things up front. What networking do I pick? How do I handle ingress? What do I do for logging? How about monitoring? Am I going to have alerting? All of those things you need to choose for on your own. So I'm here representing Red Hat. I actually joined Red Hat specifically to start working with this product because I really do believe in it. So this is not a sales pitch. I'm not a salesperson, right? I'm an architect. So my job is to make the things work. However, OpenShift has significant advantages and has since its inception. So one of the big things that is of use for OpenShift is we provide different installation methods. So there's the easy mode, which is just like, hey, point me at your virtualization API, or point me at your DRAC or your ILOs or whatever, and I'll blast my stuff on there. I'm going to give you what Red Hat decides is the industry best standard for all of those things that you would have to make a decision for, and you got a cluster, right? You don't have to worry about, am I following the tread path on this, because someone has already set out that this is going to work. If you decide to go the vanilla Kubernetes route, standing up a cluster, I don't want it to seem like a monumental thing, okay? So don't get me wrong. I'm not here to like scare you like, ooh, Kubernetes is really tough. Like, it can be. But you have to think about things like, okay, I stood it all up, but I picked Apache and I picked, I don't know, Open vSwitch, and I picked, I don't know, Victoria Metrics, because I'm in the Victoria Metrics ballroom for that, right? And so I've picked all of these things and I've installed them and I got them to work together and it's fine until you do an upgrade. And then you have to like, does this version work with that version? And this version broke my API over here. And it is a challenge. I am working with a very, very large customer. Everybody here, I guarantee, would know it. And we walked in there and they haven't upgraded their Kubernetes clusters 4 years because they can't get their mind around how do I upgrade all of the bits and make sure that I've got that compatibility. Partly because as they start to work on it, when you've got a large organization, they take a while to QA which component goes where. And they were getting to the point where it's like, oh, well, now we're installing a deprecated component. Like we're working this upgrade path to install a deprecated component. And they have to start all over again. And so the upgrade path is legitimately complex, right? The installation, not so much. It's not really scary. Lots of guides to help you with that. But when you're balancing an organization strategy on this thing that is orchestrating across your environment, and you have to make sure that these bits that you work on, the APIs match, that nothing has changed, that, you know, a very famous one is Kubernetes will enhance its security posture between releases, and that breaks things. That breaks things often. And so the pitch here really is like we test our updates. We don't push an update unless it's ready to go. It comes down almost like firmware. So essentially, because of the way we deploy it, it comes down and essentially replaces the operating system via RPM OS tree, and just splats on, and everything just upgrades to the appropriate version that has been tested. And for home labbers, it's like, but believe me, you get 10 clusters, 50 clusters, 100 clusters, that makes a big difference. So all out of the way, sales pitch done. We've decided we're going to move ahead. So what sort of architecture are we dealing with under the hood? Like, what is doing the thing? So generally speaking, a cluster is composed of at least 3 control plane. You'll also see this term, the masters, 3 masters. Red Hat prefers to be moving away to the neutral term control plane. So the documentation will have one or the other, and people often get confused about that. But essentially, there's at least three nodes in your cluster. They have a scheduler, they have etcd, they've got API, they've got controller manager, and a bunch of other stuff. Okay. Then there's another type of node, and it's called a worker node. Those handle the actual workload when you deploy something on your cluster. Now, for those people that are actually trying to keep notes, I'm going to come back to all the things that I mentioned. So I'm just giving you like a broad survey of what's the takeaway here is you got worker nodes, they handle your application, you got the control plane, and they handle the coordination of the containers and all of the fancy stuff. So the question is, when I say nodes, what am I referring to? Physical or VM or something else? So they can be physical, they can be VMs, and they can even be containers. So, however, in a general sense, you can think most people either run a VM or the bare metal. They don't necessarily. There are very few of them that run that in a container, but you can. So the way that this presentation is going to work is I'm going to walk you through various components, and the overarching theme here is we're going to talk about a restaurant so that it's a way for you to grasp how these parts go together. So it's really hard to get one overarching theme to fit perfectly for everything. So if there are people that here that really know this stuff, I know that I labor the point sometimes, but bear with me because it's meant for general understanding. So you got a node that stood up. How does it know what to do? So on top of every node, there's this thing called the kubelet. Okay, the kubelet is in charge of joining the cluster. It's in charge of establishing connection to the control plane and the API. It figures out what containers I specifically need to be running, because remember, there's one kubelet on every host. So that kubelet on that host knows what are my marching orders, what should I specifically be running. They know things like, hey, I'm supposed to be running 4 copies of this container. I have 3 and one of them's dead. I need to fix that. So the kubelet is in charge of this. In the restaurant analogy here, there's a lot of chefs in the kitchen, right? You might have a pastry chef and a chef that does chicken and one that does meat, and they all do different things, and they all have to take their orders. And they usually take their order from a master chef in the kitchen. In this case, that would be the control plane. So the control plane is kind of the master chef that is making sure that everybody in the kitchen is doing what they're supposed to do, and so on. So one of the questions that comes up is like, okay, if the kubelet on the node is the thing that joins the cluster, how do I prevent something random from joining my cluster? Like, why can't I just install a kubelet on a machine and then just say, hey guys, I'm now part of the cluster, give me stuff. So the way that Red Hat solves this is, in order for a node to join the cluster, the node first creates a certificate signing request. Then the certificate signing request is handed off to the master, and essentially, or the control plane, and it is signed with the control plane's key. And we require you to do a step that the administrator actually approves or denies the certificate signing request. If you approve the signing request, then the kubelet is allowed to join the cluster. And just as a side note, we also use the certificates that are signed as a way to protect the traffic in the cluster. So all the traffic goes as TLS. In the restaurant, this is like the security guard asking for the badge at the door, right? So the kubelet makes the application, and the signing request is the employee badge in order to show that, hey, I actually am part of this restaurant. In a tech conference, especially one like this, I'm not going to belabor what an API is. I think we all generally know what the API is. The important thing here is everything in Kubernetes goes through the API. Whether you're using a command line utility or a web page, it all goes through the API. That's just how it works. So great. I got my cluster installed, but the actual goal here is not to install the cluster. And you'd be shocked at the number of people that end their thinking there. It's just like, great, install the cluster. Here you go, people, I've showed my value. Well, no, the value is actually running the application. So that's what we want to do. So how does that happen in the cluster? Inside of Kubernetes, the smallest deployment unit is called a pod. A pod can be one or more container. By convention, you only put one in each pod. The reason for this is because the pod is considered as I guess you can consider it like a VM or a node itself, from the perspective of there is a PID1, and if PID1 dies, that's how the cluster knows I need to restart this. So if I've got a container here and this is running Apache, and I've got a container here and this is running Java, and my Apache PID is PID1 and it's fine, but the Java thing has a problem, the system does not know that this is unhealthy, because PID1 is my Apache and Apache's up. I can hit Apache, but the thing that I actually care about in my pod is actually running my Java application that people do stuff with, right? So you can absolutely shove as many containers in there. I had one client, 27 containers in a pod. That's not scalable at all. They were just like, well, we need the application to work. Bloop. Look, it worked. Yes, but if any one of those 27 things broke and it wasn't number one, your thing was dead. It just stopped working. So the other thing that makes a pod very similar to like a regular VM or a host is everything, all of the containers act as if they're local hosts. So if you attach networking to the pods, get their own IP, each pod gets an IP. That means if this is like 192.168.1.3, then each container is on that same IP because they are acting as if they are on the same local host. It's the same thing with storage. It's also the same thing as, like, in my example, if this was my reverse proxy, I hit the reverse proxy, it talks to this other container, but it would do so like like it would do the proxy localhost : its port. Is a good question. So the question was, what happens if both containers try to use the same port? Or there is also this concept of ephemeral ports that could also conflict. So this is a kind of a complicated answer, but the generic answer is the pod itself is what dictates what ports are exposed. So when a pod binds to a host, it's the pod that binds to the port. So you can't you could try, but you would fail to have port 80 and port 80 in two containers because they're sharing local hosts. It would be like you starting two Apache instances on a VM. The second one would be like, I can't. So the question is vaguely, if I've got two containers inside the same pod, how does the kernel handle the network traffic, more or less, right? So very briefly, what's happening under the hood is the kernel creates a network namespace, and then both containers join the same network namespace. And so there's no rewriting. This is a function of the kernel. And so in another talk, this may help solidify things. I show you how to just create a new namespace, a new network namespace. And in one section of the namespace, I create a VPN. And then the next section of the namespace is the exact same namespace. I launch Firefox in there. And then I launch Firefox outside the namespace. And you can see the one I launch in that namespace beside the VPN goes out the VPN, where the one that I launch just on my regular desktop does not, because the namespace is a sandbox area completely separate from everything else. So the way that it works is whichever container starts first, because there's no, without getting super advanced, there's no way to say this is container 1 and this is container 2, therefore this will have PID 1. So it's a race condition to say, like, if this container happened to come up first, then it has PID 1, and that's what is being monitored by the orchestration system. So whichever container happened to get PID 1, that's what's getting monitored by the health checks. Great questions. The only other thing to make a quick note of here is when you create a pod, if you have not specifically gone and attached storage to it, the storage is ephemeral. That means when the pod restarts, the data is gone. So that is the note here. In terms of the restaurant, pods are essentially like pieces of food on a plate. When you go to a restaurant and you order, like, I don't know, the steak, most places don't just give you a hunk of meat. There's like at least some minor attempt at a side dish or something like that. And so pods often come together in order to represent an application as a whole. So if I'm deploying my application and it needs Java and it needs a reverse proxy and a database, each one of those is a pod, and those pods, you tell it that these pods are working together as an application. And sometimes you do that in the configuration of, like, the reverse proxy is specifically tied to this pod, and sometimes you do it through Kubernetes. That's too deep for this conversation. So I've deployed an application via pods. Wonderful. What is the next step? So you can just simply push a pod out into your cluster, just like you can just start a Docker container, right? It can stand on its own. Absolutely can do that. However, that's generally not the way that we want to interact with things. So when you want to do something that is repeatable and easily understood and actually works the way that you expect, you're not going to just create a pod. What you're going to do is create a deployment. And deployment has additional information. So on top of the container image that you're deploying, it will have things like, I'm part of this network. I have this storage. I have this as my health checks. So OpenShift comes by default with a health check that just looks to see, is the PID responding? But you can also write your own health check in the case of, like, when you have an Apache server that comes up, but if this specific endpoint is not ready yet, the health check, you can write your health check such that, if I'm looking for /login, for example, and login has to be there with a login button before I want to send traffic to it, you can write your own health check that goes and checks for, does /login exist, and is there a button, right? And then if those two conditions are met, then the cluster will allow the traffic to flow. So all of these sorts of things are defined inside of your deployment. So in this way, deployment is essentially like a way to put a fine point on a recipe. So this is more about the way to kind of customize a dish. So you've picked out your dish, but this is a way for the restaurant to note, like, okay, I have 2 people at the same table that want the same dish. And so instead of writing out the recipe twice, they just put number 2 beside the recipe. Or, it denotes things like, okay, this health check with this container and this health check like this container. And that is, again, like a customization where the waiter will just be like, oh, this person wanted onions, this person wanted, I don't know, sauerkraut or something like that. So I now know how to deploy, generally speaking, and provide networking and storage. So the next thing is it needs to get onto the cluster somehow. So how does this work? There's something called the kube scheduler, and the kube scheduler acts as the hostess. So they get a request. So you've now made your declaration, I want a pod, or I want 15 pods, whatever it is. The kube scheduler then looks at that and adds up the amount of CPU and RAM that it thinks you need, or you've explicitly told it because you can tell it how much you think it needs. It looks at affinity or anti-affinity rules to make sure that I'm not sticking things where I shouldn't, and then it basically sorts around the nodes, ranks them, and then deploys them, right? So in Kubernetes, the entire cluster is a pool, and this is a very difficult concept for traditional sysadmin to get a handle on. I have people that will call me and be like, 80% of my load is on this node, and I'm like, okay, but your entire cluster is 10% loaded, so why are you calling me? Well, it shouldn't all be on this load. And like, well, aside from anti-affinity rules, there's no reason why it shouldn't be there because the cluster is viewed as a giant pool and not individual nodes on the cluster. So if for whatever reason that had the fastest networking or the better storage or whatever ranking that the system decided to use, it will just put them wherever it wants. There is a button that you can push now that will kind of kick to try and level that out, but that came really late because that's not really the way that it works when you're considering the cluster as a pool. At any rate, so the kube scheduler is basically the hostess that looks around and figures out which table to seat you at. So, great, I've got a container. Container's got stuff. It's now been assigned to a node. How do I get traffic into it? So this will be the first time where we've actually have a little bit of a divergence between Kubernetes and OpenShift. Because Kubernetes allows you to pick all of the building blocks, or I should say requires you to, you have to get traffic into your cluster somehow. So in this diagram, what you're seeing is like this person's generating traffic through the internet, and we've picked the Nginx controller as the way to get information from the outside into the cluster. The cluster is running on a software-defined network that is not routable. So you have to get traffic into your cluster, and the traffic has to come back out, and that requires an ingress controller. So you have to set this up on your own. You have to pick them. It could be Nginx or traffic or MetalLB, or there's all kinds of options, and they're all fantastic, right? The features that you get in terms of networking depend on the ingress controller that you pick. So some good thought needs to be put into this because some controllers. So when you are passing, for example, TLS traffic, there's three common patterns. You've got TLS pass-through, where the load balancer just steps out of the way and sends it right on into the container, and the container has to have a cert. Then there's TLS encryption, which is just the load balancer presents the certificate, and then there's re-encryption, where maybe your organization has requirements to be able to look at the data as it comes in. So from the outside, you've got a public cert, and then it hits the load balancer. The load balancer encrypts it with your certificate so that your networking equipment can do deep packet inspection or whatever. So those are the three general ways of how TLS traffic flows into the cluster. And all of those depend on the choices you make right here for this ingress controller. So something to think about, on top of the fact that you'll also have to figure out, how do I rotate my certificates? If the certificates live on the ingress controller, how do I rotate them? Like, you need to think about all those things. OpenShift has made this decision for you, so we prefer HA proxy. So with that, we've already integrated things like the certificates rotate on their own. All three of those options that I mentioned exist and are just a drop down in the menu when you're creating your application, should you like a GUI. Also available on the command line. And there's a tight integration here. So there's this other concept, not another concept. There is a joining concept. So a route is basically a URL that you give to the outside world that gets to your cluster. And then the load balancer goes, great, where do I send this traffic? So in order to know where to send the traffic, it uses internal DNS. And in our case, in OpenShift's case, we use core DNS. That's just kind of an implementation detail. But the point is essentially whatever ingress controller you use is functioning as a load balancer. You need to have a backend for that. The most reliable way to have a backend is to use DNS names, just like you would for servers. You don't want to just tie IPs to that. So in order to accomplish the mapping of the DNS name to the internal server IP that gets assigned to the pod, there's something called a service. Okay, so the service is your internal DNS, and its sole job is to map the DNS name in the cluster to the IPs that the pods have. So the route, what happens is I call www.mycluster.com, that gets to the load balancer. The load balancer then looks and says, okay, I know that that route is associated with a service that has a name, like my awesome app. So the route connects to the service, and the service is like, okay, I know that my awesome app has these containers that are part of my app, and it will direct the traffic appropriately. Are we clear on that? Okay, so in a restaurant, the way that this works is, don't skip past the slides, Steve, that's bad. The restaurant is kind of like the route is a menu that everybody can look at. You don't have to know all of the bits that go into making your enchilada or your chicken salad, right? You just know that you want a chicken salad. So that's what the route does. The service is the waiter, and the waiter knows, hey, if they order an entree that has a steak and they also order, I don't know, pastry or whatever, it knows I need to split that up into the different chefs in the back. But you don't have to know anything about that. You just tell the waiter, I want these things, and the waiter goes and figures that out. So how does traffic flow? Traffic flows by this process called the kube proxy. Now, I know I'm going fast, so I talk fast. I also want to try and give people time to ask questions. Feel free to interrupt. But the proxy runs on every node in the cluster. Okay. The proxy's job is to implement the service. I know that's a little bit confusing. We don't need to dive into that too much. In our analogy, the kube proxy is essentially like a computer program. So in a restaurant, very few restaurants have the waiter take down the note and actually stick the note on the little turnstile and turn it anymore. Most of the time, the waiter writes their notes, and then they go to the computer, they type the order into the computer, and then the computer goes and puts it up on a screen in the back. That's what kube proxy does. So what happens is the waiter comes and types the information into the system, and kube proxy is the system. It's like, okay, I know I need these backends, and it takes that order and makes sure that, okay, well, Apache is in this container, it gets this traffic, and the DB is in this container, and it gets this traffic. So it's the computer program that ensures that the food item gets placed on the right screen in front of the right chef in order to do the work. So this is the point where we take a break, because I talked a lot and you can ask questions or get up, but take 5 minutes and I don't know, chat or don't, and we will continue in about 5 minutes. All right, I'm going to kick off again. Y'all can continue having your conversations. It doesn't bother me, but I'm just going to keep talking. So we'll be competing, and I'll probably win because I'm louder. So we've got our application out, and we're getting traffic into the application. But as I said, the applications are ephemeral. And so the next thing that you have to think about solving for is storage, right? So when a pod moves around in the cluster, what's actually happening is the pod is being killed and then recreated. It's not actually doing a vMotion or any kind of live migration. It's basically being shot and restart on the other side. Now, there's some knobs that you can twiddle that'll say, like, don't touch the pod until this one is confirmed to be able to handle traffic. And like, you can do lots of graceful stuff. But what that means is you also don't have any control over with a caveat, when the cluster is going to decide to move you around, right? So the hostess comes in and you're sitting at a table of 6 and there's 2 of you, and somebody comes in and they've got a party of 5, they might be like, we need to move you over here. And this is where the restaurant analogy kind of falls down a little bit, but the cluster is going to rebalance itself, and you shouldn't care, and you largely don't have much control over when it decides to move a pod around. And that means if you're relying on storage, it will go away. So the default storage in Kubernetes is called empty dir. Very descriptive. Hint, hint. So the way that you get around this is by setting up a persistent volume. And again, very descriptive. So a persistent volume by itself doesn't help you. Persistent volume is essentially a pointer to where your storage lives. So you can think of this like an entry in your FS tab, for example. By itself, it doesn't do anything. It actually has to be mounted before it does something. But the volume is a pointer to where the storage would exist. So I can call my NFS mount or my CIFS mount or whatever, and you kind of call it dynamically. So you would define a persistent volume. The way that you connect the persistent volume to your pod is through a persistent volume claim. Okay, so essentially what happens is when you create a deployment in order to deploy your pod, you would actually say, this is my storage claim. And that storage claim has the definition of the storage, the persistent volume that you've created previously. So it links them up. One claim can only ever be bound to one persistent volume. If you try to bind mount 2 things to the persistent volume, it will fail. With a caveat, there are different types of storage that are available. So you can do read write once, and this means it can only be mounted to a single pod at a time. You can do read only once, and obviously this is just, hey, make it read only because I don't want to actually be able to mutate my data. And you can do read write many, and this is where multiple pods can read and write. But what I said still holds. This persistent volume claim will not bind to multiple persistent volumes. It is a one-to-one relationship. And you'll actually see in the status, this will say, I'm bound. And the persistent volume also will say, I'm bound, and it will give you a list of things that it's bound to if it's read write many. So what's important and very difficult for people to wrap their brain around is that all of this information is metadata only. So you can create a persistent volume and tell it, I've got 10 terabytes, and it's 10 megs. And the system will get, cool, right? And you can also do the things like, this thing should be read-only. And if your storage is not controlling for it, and the pod wants to write there, it'll be like, cool, no problem, because it's just metadata. The metadata is meant to help the system link volumes to claims. The reason for that is, if you are doing this and you're pre-provisioning tons of volumes so that you've got lots available for applications to claim, it's going to try and find the best option. So you might have 5 gigs, 10 gigs, 15, 30, and 50 gigs, and something calls for 25 gigs. It's going to look for 25 and above, and might even pull the one that's labeled for 50 because it matches that criteria. Yes? It is not an enforcement mechanism. That is correct. Your storage still has to do the controls. There's a caveat here. Inside of OpenShift, we use SE Linux, and SE Linux labels everything. And anybody who's fought SE Linux will know it will not let you do anything, ever. So there's some there are caveats here, but speaking in generalities, right? You still have to control, like, if you say this is 50 gigs, and you actually have 10 terabytes, it'll let the pod continue to write into infinity as long as the storage will let it write. So you're still having to interact with the storage team. You're not going to get away from that. I say that, and then I'm going to tell you about this. There's something called the CSI driver. CSI drivers are storage drivers for specific backends. MinIO, OpenShift Data Foundation, NetApp, all of these sorts of things. They're essentially API calls to a backend storage. So in that regard, your question is what I told you about the storage is correct, but if you're using this method, the API is going to block you. So if you go and create the persistent volumes, there's no controls there. That's just metadata. If you use the CSI, which is an API call to your backend storage, that will block you. Does that make sense? So ultimately, this is the way that you want to go if you can, but it is a driver. So the driver has to be available from your vendor. There's not much we can do about it. This concept is both OpenShift and Kubernetes, whereas when I was talking about Kubernetes, OpenShift will block access to files via SE Linux, and that's an us thing. Unless you install SE Linux on Kubernetes and then go ahead and figure out how to configure that. Good luck. So I've got storage, I've deployed things, I'm getting traffic into my cluster, everything is going great. Anybody who's played around with containers knows that if I need to make a change, I probably have to rebuild my container, even if the container itself has not needed to be updated. I need to bake in a new config or whatever it is. There's an easier way. So Kubernetes allows you for a dynamic configuration injection via two different methods. So the config map. This is pretty much what it sounds like. A config map is a specific object in Kubernetes that allows you to stuff an entire configuration in there. Go nuts. Caveat. This is not space sensitive. If your configuration is space sensitive, YAML, this is going to make you fall all over the place because you'll shove it in there and it'll just treat it as one giant glob of text. Same thing with certificates. Certificates will fail because they're also space sensitive. So this is really good. Like a config map is good, right? There's nothing wrong with this. You can you can change environment variables. You can inject entire or parts of configuration files. You can even put binary data in there if that's how you roll. Not exactly sure why you would do that. It's not true, but I think it's silly. In the restaurant analogy, the config map is basically analogous to, hey, I want to cook some eggs, right? Do you want them over easy, over medium, over hard? They don't rewrite the recipe. They just say, hey, flip it over for 2 minutes. And so it's a shortcut for, it still knows how to make the eggs. You're just flipping it over for 2 minutes or 4 minutes or whatever. So you don't actually have to rebuild your container. So there's also this idea of secrets, which is terribly named. It is not actually secret, okay? So I'm going to first tell you the analogy, and then I'm going to tell you what a secret does, because it'll be a little easier to understand. So a secret is essentially like having a locked door with your most precious recipes laying open on the desk. Anybody who has a key to the door walks in, walks out with your recipe book. That's what a secret is. The reason why it's called a secret is because most objects in Kubernetes are mounted on the host and then into the container in some process. Secrets are done in TempFS, so they never actually reside on the host, and that can be very important for security individuals. However, secrets are widely used because they are base 64 encoded. If you've not worked with this, this means it preserves exactly what you type. The number of, whether you use spaces or tabs or whatever, it uses exactly. So certificates, usernames, passwords, YAML files, those things that are really white space sensitive go in a secret. But anybody who has any kind of elevated privilege in your cluster will just be able to click reveal secret, and there it will be. So they're not secret. How do you get around this? Well, one of the things you can do is integrate with a third party. So HashiCorp Vault is the leading thing out there for doing secret management. This is not a sales pitch. I just like it. It's also open source, so I actually run it in my home lab because you can just go and grab the container and run it, right? Let me rephrase that. It is source available until a certain point. They have it built into their EULA that after a certain point, it actually becomes Mozilla licensed. So it eventually rolls into a full open source license after so many releases they've moved forward. Whatever, I don't have the exact details on that, but so it's source available if you want the current version, and if you want the actual open source version, it will be several versions behind. But they have been consistent in making sure that they are rolling their source available into open source. But back to what it does. So this actually gives you a centralized place to store your usernames and passwords. I guess it's kind of like Bitwarden for the enterprise, although it does a bunch of fancy stuff. So it can create a dynamic secret. So I know it knows you're spinning up a database, and if you say, give me a secret to generate the database username, it'll do that and then store it for you. So you don't actually have to generate it. Like, there's a bunch of stuff that it does that really helps, including the ability to automatically rotate any secret that it has. So if it's storing a secret for you and it's storing it in and you're using it in OpenShift, you can actually tell HashiCorp, go rotate all of my secrets that OpenShift is holding. So there's a bunch of stuff. It doesn't get around the fact that secrets aren't secret, but it helps a lot with the mitigation should you need to roll those over. So now we're going to get into how do you constrain your application. This has a couple of different vantage points. So number one, you're thinking about security. I've kind of touched on that already. SE Linux exists in the picture, and in our recipe, or in our restaurant, pardon me, in my restaurant analogy, you've got all these chefs, and usually they actually have pre-prepped all of their ingredients at their stations. And SE Linux basically stands in the kitchen and makes sure that the chef doesn't steal, ingredients that somebody else prepares. So he's just standing there and saying, nope, can't do that. For those of you that don't know, SE Linux is a security-based module that essentially applies labels to everything on your system and then allows access or not based on the label. OpenShift does this by default, and it labels everything for you by default. And so that allows you an extra layer of security. It's actually saved us from at least 3 different CVEs that I know of in the last 5 years, where there was a container breakout in either Docker or run C or container D, because you can break out of the container, but SE Linux is not going to let you go anywhere with that. So you breached the container, but you weren't able to do anything further because SE Linux is standing there going, nope. Sort of related to that, anybody who's run Docker knows that it wants to run as root, and it will do whatever it wants as root, which is fine, right? It runs privilege ports, and it will run UIDs that are part of your system, right? Apache or MySQL or whatever. OpenShift doesn't allow this. So we enforce rootless containers by default. The UIDs that we use are above 1 million, so you're not actually ever going to conflict with UIDs on your system. That might bite you in your storage area if you're trying to make sure that the storage gets very confused if you give it like, hey, this guy's got a UID of 7,305,000, and it'll go, what? So there's some little foibles here and there, but by default, Kubernetes does not restrict this and just allows you to do whatever, whereas OpenShift restricts it, and then you have to jump through hoops and say, yes, I'm really sure I want to run a container as root in my cluster. So moving away from security and thinking more about running applications and being a good neighbor, or preventing noisy neighbors, perhaps is a better way of thinking about it. There's these 2 concepts of a request and a limit. And these specifically have to do with the resources that are available to the container. So a request is your reservation. You call up and you book and you say, I'm going to show up with 4 people, right? And they schedule your reservation. The Kube scheduler decides where you're going to go, reserves your spot. You show up with 8 people, and one of 2 things is going to happen. They're either going to say, sorry, you'll have to go somewhere else, or they're going to say, you can only have 4 people, and you have to split your party. And that's what limits does. Limits is the maximum party size. So a request is like, I need to have a table with at least 12 people. And if you don't set that, if you don't set a limit, OpenShift will just look at it and go, okay, you need at least 12. Well, here's 25. That'll work because that's more than 12. So there's the counterbalance of limits, which is just like, I want to make sure that this application that I know is really greedy gets from a minimum of 4 cores that it needs to start, but I don't want it to eat more than 12 because it's going to just starve everything out. So how does it keep track of all of the stuff going on in the cluster? There's a cluster database called etcd. This runs on top of the control plane. etcd tracks everything, and I mean everything. It has your secrets, it has the API calls, it has which nodes and what state they're in, it has what applications are deployed to which nodes, it has what IPs are floating around, everything, you name it, it is stored in this database. Therefore, you don't want to lose this database. It's very bad. It runs as a cluster of 3 by default. You don't have to do anything in OpenShift. So in Kubernetes, there is some setup here. It's well documented. It's easy. Don't want to scare you or anything like that. In OpenShift, we just decide you get 3 by default. You can make it 4 and you can make it 5. Don't do that unless you know what you're doing. When you're dealing with distributed databases, the more nodes you add, the more latency you add across the cluster. You should only do that if you know that you need that. But having said that, going to the restaurant analogy, it's essentially like a security system or a giant ledger that's literally tracking everything in and out of the restaurant, what food is delivered and how many tables I have and all that sort of stuff. As a final note, the best practice is take backups of your etcd. I would say off-ish the record because I'm actually on camera. It doesn't do you much good because it tracks the current state of the system. If you take a backup of your etcd and then you have a failure a week from now, you're going to restore a state of the cluster from a week ago. So pods are not going to be like etcd is going to think of like this pod is on node 1 and now it's on node 7. And it comes up, like the database will come back up and think things are all over the place. So it is a good idea to take this. This is a check mark that you want to have. Yes, I am taking a backup of this. It has limited utility in an emergency. Red Hat experts, which are not me, I've been on these calls. We had a client that preferred for us to spend 7 days, 24/7. Literally, we activated people around the globe to restore the etcd database because it was going to be much harder for them to reinstall the cluster, which is a thing in and of itself. But to give you some idea of the scope of what you're tinkering around, someone with database expertise actually has to go in to individual tables and columns in the database, change this, tinker this, do this. There are very, very few exceptions. You should not do that. Right? You should never do that. And definitely do not do that without someone, Red Hat or your service provider. Do not do that. So all of this comes together to make a system that has a declarative state. So when you are saying, I want X number of pods, it's going to continuously watch to see, can I bring these things up? I'm going to always try to be at the state you told me I should be at. Okay, so the desired state. The desired state is handled by something that are called controller managers. This is a broad term, okay? So it's a category of things inside of Kubernetes that keep an eye on specific sections. So you've got a replication controller, you've got the node controller, a service controller, you get the point, right? And so each one of these are specifically meant to ensure that they are looking at just their section. And yes, my service exists and my service has a back end and I have this many things in my back end, or I'm a deployment and I want this many pods and yes, I have this, or no, I don't. And that's all that these things do. And so essentially they run in a loop. I want to say it's every 5 minutes. Don't quote me on that, but I believe it's every 5 minutes. And so they run in a loop, they do their check, they go to sleep. And every 5 minutes they wake up and they do their check. And so this make sure that everything is functioning as possible. And this is kind of like the manager at a restaurant. They are not only checking to make sure that the food is being delivered, that the wait staff shows up on time, that I have enough staff, but they also do things, and this is where I'm going to stretch my analogy just a tad. The manager in the restaurant cares about whether or not the food gets delivered properly. And what I mean by that, in a restaurant, we've all been there when somebody's dropped a plate. The waiter takes down the order and puts it in the computer. Then the chef makes the food, puts it up, ding, come pick it up. Everybody in the chain has think they've fulfilled their duty, and somebody, usually not even your server, brings out the food to your table. And if they drop it on the floor, well, your waitress is at another table, the chef has moved on to another thing. Who makes sure that your food gets brought back out to you? Because it's not your fault somebody dropped it on the floor. Well, that's what the controller manager does, right? He's the manager and makes sure, hey, that guy needs more food. Hey, you chef, you're open, start making that new food. So we ripped through the back half of this because I didn't talk as much as I thought I did. So this is kind of the start of the summary slide. So I'm going to kind of tie my restaurant analogy together for you, right? And kind of as a summary. So at a high level, there's the kubelet, right? The kubelet is the thing that the chef that is responsible for making sure that all of the food that he is making happens in the kitchen. He's preparing the dishes, he's taking the order from the master chef to make sure that everything is working correctly. Joins the cluster, has the number of pods, and so on. In order to make sure that no one just installs a rogue kubelet, you've got the certificate signing request. And this is just essentially issuing you a security badge. You've got the pods, we've talked that to death. We now know what a pod is, but essentially these are the dishes that come out that actually make the application work. The deployment is like the recipe card in terms of tying everything together. What kind of storage do I have? How many pods? What container image? All of that sort of stuff is the entire sum of what's going out to the table. You've got the scheduler, and the scheduler is the hostess assigning things. You've got the route, and so the route and the service are often still the most confusing for people. The route is the vanity URL that someone resolves to your cluster, and then the service takes the information from the route and makes sure that it gets to the correct pod. You've got the kube proxy, and the kube proxy is that computer program making sure that it is being displayed on the heads-up display at the right place, ensuring the traffic is flowing throughout the cluster, right? We talked about the config maps and how the config maps are basically just a shorthand to change environment variables or little bits of information inside of your containers so that you don't have to rebuild them. Then the secrets, which are not secrets. Normally I run a poll just to see how many people are paying attention. Is a secret a secret? I did not do that this time. Anyways, moving on. That is correct. A secret is, so both a config map and a secret are essentially a bind mount into the container. However, a secret is a tempfs file system that is being bind mounted into the container, whereas a config map is usually literally like taking a file and mounting a file on top of another file. And then there's what's called a reconciliation controller, which is watching for those changes. And when you apply something like that, it's like, oh, I need to go reload my config. And sometimes that's, if the application's smart enough, it'll kick the actual application without restarting the container. But in most cases, the applications are still not Kubernetes aware. And so it will actually, I have to restart this. And so that means bringing the container down and back up again. It's a good question. So then getting back to the kind of the summarization, non-root containers are enforced. You've got SE Linux for the security, and everything runs through etcd. And ultimately, so this is why it's kind of a survey topic, because we sped through lots of these things, and I just wanted to give you the pieces of information that if you wanted to go and hunt up more information for yourself or dig deeper, you kind of know what to look for. Because one of the hardest things is how do I know what to go search for, right? What pieces do what? Where do I get this information to even dig that out? And so kind of with that in mind, if you're interested in going beyond the 101, right, you have to start thinking about things like the identity providers, right? So I want to be able to allow people to log into my cluster, and usually that's through Active Directory or LDAP. These are things that you have to bring on your own. There is no identity provider. No, that's not true. There is no centralized enterprise identity provider by default in Kubernetes. OpenShift by default supports LDAP, Active Directory, GitHub, GitLab, Google, OpenID, Keystone, and a whole bunch that I'm not remembering. Those are just the ones that are like common that I remember. On top of that, so you've now logged into your cluster with your enterprise ID. Are you doing it via the UI or something else? There are a lot of projects out there that will provide you a level of UI on top of Kubernetes. You have to choose that, and you also, they're not as well formed as what I would like. And maybe I'm spoiled because I've been working with OpenShift for almost 10 years. But our UI it really is good. It's not a sales pitch. It's just when you've used it and then you go somewhere else, it's not even a comfort thing. It's just like the features are just not there. And they'll get there. It's kind of like Cockpit and having modules for Cockpit, right? They're not there out of the box. You might be able to find it somewhere. It's the same thing for Kubernetes. It's not there. It might exist somewhere out in the wild, and it'll get there if it's popular enough. Think about your observability stack. So we ship Loki by default. So this Loki helps you handle logs and alert, well, not alerting, that's Alert Manager, but logs and metrics primarily. I know I'm in the Victoria metrics room. Sorry, guys. We ship an alternative product. It is what it is. And the other thing is we have a pre-baked logging stack, and that is that can be a big boon. It depends, right? If you're heavily involved in like Splunk, you probably just completely ignore or uninstall that component and stick the Splunk Connect on there, or whatever they're calling it these days, which is fine. Use what you should use, but the things you need to think about when you're doing the enterprise orchestration, you still have to do that. And the other thing, so one of the things that is missing from Kubernetes is multi-cluster management, because likely you're going to have more than one cluster. We have a product called ACM, which is the Advanced Cluster Manager, and it gives you one spot where all the metrics get funneled into, and a bunch of other, it gives you a quasi-Active Directory, like it's got a policy engine that you can write policies for that push out to your cluster. It's obviously not as well formed as Active Directory because that's 20 years ahead of us. But the point is like there is a centralized policy management tool that's there that includes centralized Argo CD if you know what GitOps is and you care. That's also baked into the cluster management suite. And the other big thing that may, and this is a specialized case, but if you have a situation where you need to install the cluster and operate the cluster without internet, vanilla Kubernetes is not going to get you there. So they don't have a well-defined or documented what's called air gap solution. You have to roll your own. Because you're assembling all of the pieces, you have to go to Nginx and be like, how do I run you off? Like, how do I get your images offline and feed it into the cluster? Like, all of those pieces come together. And because vanilla Kubernetes, you build your own, you have to pull all that together. Can you do it? Absolutely you can, right? You just have to figure out all the bits that I'm going to use, and then how do I make all of these bits work offline without, calling home or whatever. Whereas OpenShift has documented, well-trotted air gap because we deal with governments, and we're on cruise ships and submarines and like all kinds of places that I wouldn't have even imagined before starting here. And there's no internet. So it is a well-trotted path. And with that, I will end this a bit early if there are questions or we want to chat a little bit more. Otherwise, I wasn't sure how much I was going to talk today. Are you the mic?
When would it be appropriate to, or I mean, I'll ask the question the other way around. When would it be inappropriate to put something inside of Kubernetes or containers? So, for example, you have this big monolith that is from legacy times and all the things. Is there a time where you would say, don't use Kubernetes for that?
That is a really good question. I have to think about that. The problem is there's almost always a reason to do it, depending on, so like for example, I'm going to take your question, go on a little tangent, I'll come back. So OpenShift can run and does run as a hypervisor. So you can run your VMs on top of that. So then the question would become like, well, why am I going to run Windows VMs inside of Kubernetes? And the answer to that is because when you treat your VM like a Kubernetes object, it means that you can insert that Windows VM into a build pipeline and inject your configuration by a config map or a secret, or you can hook up dynamic storage to it depending on the situation, right? Where you're taking this legacy crufty old Windows XP machine, for example, that you have to have because it's a vendor requirement. It runs some $7 million machine in the back. I need to do something with it, but I want to kind of treat it more modernly, right? How do I make it move around? How do I make sure that, like, how do I adjust the config files inside of it without actually having to interact with it, right? That's what Kubernetes allows you to do regardless of the operating system. So back to your question, when is it not appropriate? I would say that there is a heavy weight of infrastructure in order to stand up a cluster. And so if you want to run 2 or 3 containers or even 2 or 3 VMs, it might be a pretty heavy lift just for that. There are single node installations, but you give up like a lot of what makes Kubernetes worthwhile running. So I would say if you don't have, like, I don't run Kubernetes outside of my lab for work. My home stuff runs on KVM because OpenShift is just too fat. So is Kubernetes. Like the requirements to run a distributed database just to run VMs is just too much. Yes. Oh, well, looks like somebody else had the mic. You didn't have your hand up, sir. You tried to jump the queue.
Thank you.
Oh, I see. I thought he was. Anyway.
It always seems like I see whenever somebody's use case gets really, really big and messy, they end up with lots of clusters. I never see one giant cluster or with tens of thousands of nodes, and I never see like a single cluster with distributed nodes. Is there any use case at all for a single cluster with distributed nodes? And if not, what's the Kubernetes internal reason why that's a terrible idea?
So if you're talking about distributed nodes like across data centers or things like that, so your main challenge is how do you replicate the storage? So storage is a primary concern across there. Do people do it? Yes. You have to have a stateless application in order to work that appropriately. Do we have people that, is it a valid architecture to have a distributed cluster in general so that you've got a control plane and some workers in various places? Absolutely. But then you have to treat them as failure zones, right? So if you lose connectivity or you need to shift, like ultimately you wouldn't be shifting things from quad 1 all the way to quad 4 because the storage latency to make that happen would just, it wouldn't be feasible unless you're in the same building and you could run fiber there. Because essentially what happens is the networking has to unattach from here and reattach over there. And so either you've got crazy bad latency on your network because it's in a centralized place, or it's having to do storage replication in the back end to get that information over there quick enough for that to be feasible. Does that help?
Okay, I have 2 questions. The first one is bouncing off of Noah's in that, esoteric Windows XP machine. You said earlier that Kubernetes is like, okay, it's down here, I'm popping it up over here. No vMotion, no whatever. Wouldn't that cause a lot of issues? And wouldn't that be a reason to not use Kubernetes? If you have something that has to stay up, perhaps it's running some, like you said, some software for a thing in the back that's got this old database on it and you just don't want to shut that down and spin it back up over here?
So the answer to that is it depends whether it's a VM or a container.
Say it's a VM.
Okay, a VM, what happens in that case, and you've decided that this has to be up, it will spin up a libvirt container on its target destination and then do a live migration from libvirt here to libvirt there. And it does that on the fly. So it will migrate in that case. But the pod itself does not recreate. So a pod that is running the VM does not just move. What happens is it creates a new pod over here and libvirt, and then libvirt says, start transferring me the information, right? And then it gets all the information, then it does the final memory copy, shuts this one down, and has that one running, and the networking takes care of doing that A/B switch.
Okay, and the other one might be a question that's too advanced or not relevant to this, but you want to start and you have 4 servers and they've got nothing on them. What is the underlying core that starts to, because you said you could go right into the IPMI and blast Kubernetes to it. Well, you've got to blast something. What does OpenShift use? Is it like I'll just let you answer the question.
Sure, yeah. So OpenShift uses CoreOS, so specifically RHEL CoreOS. There is Fedora CoreOS and there's RHEL CoreOS. And RHEL CoreOS, both of them are RPM OS-based distributions that you can think of largely as like firmware. It just splats it on there and it has everything it needs to run the system. Minus it will pull the latest containers from its registry. As the administrator, you mean? You don't. It comes down as a firmware as part of the OpenShift version that you're running. So if I'm running 4.18.4, it has this version of CoreOS that comes down, and you don't. So no, it does it for you. So it knows if you're running a VM, and it knows that if you want to live migrate, it needs to spin up a libvirt, configure it, join that libvirt to this libvirt, and they form just a single one-to-one cluster for the live migration, and then this one shuts down. Oh, well, so like OpenShift's web UI is encompassed in that. So, well, but you don't have to do anything for that because when the masters are installed, they get the web component installed as part of the package that comes with them. I don't know. I haven't used Proxmox. I'll say sure. It's like Cockpit, right? Most RHEL boxes come with Cockpit installed. It's just, yes. He's got the mic.
So I had 2 small questions. Forgive me.
I can hear you.
Okay. So they're a little bit minutia. First of all, you mentioned with the etcd database that it's a good idea to back it up, but in practice, sometimes that doesn't actually help when it comes to needing to restore. How big is your average etcd database, and given the size, would it be practical to back it up literally like every minute, every 5 minutes, whatever?
So the average size is between 2 and 8 gigs, depending on how busy your cluster is and how wide it is.
Gotcha.
I would say I wouldn't do it every 5 minutes, but we have people that do it every hour to an S3 bucket, for example.
Gotcha. Okay. And my last question is, you mentioned the certificate requests as the method which the master, allows or denies a new host to join the cluster. If you have an organization which is a little more stringent about their certificate request mechanisms, is it possible to use existing certs and keys if you already know the hosts that are going into the cluster, for instance?
So you can use your own certificates. I wouldn't, but you can. So, okay, let's split this out just to be absolutely clear. There's certificates that are used for the cluster communication, and then there's certificates for the application communication, right? We're talking about that lower level. You can do that. However, if you miss rotating them, your cluster is broken immediately, right? And in some cases, you might even have a situation where something freaks out because it's within 2 days of going bad or whatever,
So
right?
it's a situation you'd lobby for using the cert request mechanism that's already there.
As strongly as possible. I've had 2 customers, I think, that have used their own, and it was due to regulation that they needed to do that.
Okay, thank you.
Of the database, could you, if you have 3 copies of the etcd database, can you put them in 3 different areas?
Yes. Yep. The only thing that you have to be concerned about is the latency, because essentially it is a cluster database. One of them is elected as the leader, and then it takes all of the writes and sends the writes out to its we used to call them slaves. I don't remember what it's called these days, but it's surrogate, the read-only copies, right? The further you put them away, the more latency and the longer it takes for them to catch up on the data that is being written to the leader.
Yes, and are you worried about there being a change that kind of fundamentally breaks the database, or do you think you'd normally be able to restore from a copy?
You can almost always restore from a copy. So if you have at least one standing control plane, you can go and dump the database.
Okay.
Which is also why you're in a real bad way if the only thing you have is your only backup copy.
Hi, I know this is a beginning one I really appreciate. This is a great overview. Question is, and I think it's relevant to people that are just learning it. Where do you see this going in terms of career and for people like people who want to learn it? And I'm specifically with regard to machine learning. Somebody asked a question about scope. So, once upon a time, they told us don't ever put databases in Kubernetes because it was bad. Now it's everywhere, right? It's bundled with hardware, et cetera. And I know I'm kind of paraphrasing.
Yeah.
And now, we've got H100s in our cluster that are running, these massive $31,000, machine learning jobs. My point is, how do you see this in terms of to help people guide their choices about what with OpenShift when they learn it? And kind of in that question is, what do you think Red Hat's going to go with the machine learning support, with given the fact that OpenAI is, all on Kubernetes and everything?
Well, so we actively support machine learning and have for a long time. I myself have been deployed to do machine learning, which is adjacent to but separate from AI, right? And we also have OpenShift AI just as a familiarity point, right? So we've had machine learning for quite a while, and now we've had OpenShift AI since the start of last year, give or take. So in terms of the direction, we fully support all of that sort of stuff, with the caveat of you might be doing something that is not currently supported AI moves, right? But did that help answer that part of the question? As for the comment about the career, that's a good question. Part of it is what do you want to do? Because OpenShift or Kubernetes is not going to eat the world. It is, if you want to work in a segment of the population, it is going to be very prevalent, right? Just like there's always a specialization for Windows servers, right? Linux may have eaten the internet, but there is a heavy demand in certain segments for Windows things. And it's the same thing with Kubernetes or OpenShift, right? The governments, in particular, governments and financial institutions are really interested in this because they can squeeze the resources. They basically collapse their VMware people and their container people into the same people, and they really like that. So it's a good career move if you can get ahead of those people.
Somebody asked, I found that Kubernetes is kind of like an enterprise JVM, and let me justify that statement. Somebody was saying, how do you tell whether you scale, how much to put in it? Do you say one cluster? What's this multi-cluster stuff? Which is kind of where we're going. If you recall Java, it was going to be the write once run anywhere thing, and then people wanted specific things for their applications, and so they started bundling the JVM with them, and now they bundled Eclipse with their applications and stuff. And I see this happening in the enterprise level. So, for example, Domino held everything back in our particular enterprise.
Yeah.
So we had to roll another cluster immediately. So basically, it's the same problem. It's just at enterprise scale.
Yep. Yep. You're right about that. Yeah, it was my computer going to sleep, not the projector. Good questions. I'm happy with the engagement. Thank you for asking questions. That makes me feel better because there's nothing worse than like having people show up and then everybody just leaves without saying it. Like, you don't have to say thank you, but it's nice to actually get engagement. So I'm happy to field questions.
So we're just starting to look at OpenShift for our next deployment, and we're a big HPC shop, and wondering, is this appropriate for HPC workloads that use a scheduler like PBS Pro or something like that? Oh, okay. Yeah.
Yeah, that gets a little bit more out of my depth. I would say that we have a strong partnership there, and there is a lot of work that goes on. That honestly, outside of my skill set,
Yeah.
I'd love to answer that question for
Sure.
you, but
Like parallel stuff, a job will use 20, 30 nodes or something like that. So
yeah, and the problem is like I'm familiar enough to talk with you about it, but like I can't actually answer those questions with any authority, right? So
oh, thank you.
yeah, that sort of thing is a type of conversation that usually takes a couple of months to sort around. Where honestly, like a lot of those questions are it's not so easy as answering a generic answer, right? It's like, well, what are you doing with it, and what can you part with, and like, what absolutely has to stay there? Because sometimes you can tease apart like this is really important to us, and we can make that link and put the effort in, and this is less important, and we probably don't want to put the effort in on that segment, right? And usually it's a blend of um, working with Big Iron and OpenShift in combination instead of just like flattening the playing field across the board. Yes. Yep. So it uses the Redfish protocol, which allows you to talk to like Supermicro, like DRAC, ILO, BMCs, like just across the board. It uses the generic language. What's that? I'm not familiar with those there, but you phrased the question a little bit different. Maybe I have a better answer. Uh, oh, Talos. Okay, now I'm tracking. Yes, yes, yes. Right. No, that yes, we are. It's similar to Talos, except you have SSH access via the key that you bake in during the installation process. Yes. Yes. That's kind of considered the break glass, though. Like you really shouldn't be SSHing into the box, but if you have to, you need that SSH key to get in. Yeah. All right. Well, party on, folks. You're done.